Hello and welcome to this brief presentation related to technical report writing. Within this presentation we're going to consider an example structure for a stress analysis report within which we're going to undertake a comparison between the results from a CAD-FE model and the results from classical theory, in other words hand calculations. Note for reference, the acronym CAD means Computer Aided Design, a typical software package used for 3D modeling, and the acronym FE means finite element. In other words, in this case, the CAD model is analysed using the inbuilt finite element software. The computer aided design model we're going to consider relates to the simple bracket shown at the bottom of the slide, which has 1 point load applied shown here and is restrained in this region shown here. It should be noted that this presentation is aimed at students studying the HNC or higher programs, and so does require a background in mechanical principles at the HNC/HND level. Here's a brief presentation overview of the simple bracket stress analysis report. We commence with a brief introduction that outlines the background to the report in this presentation, and the overview is why we need to verify CAD finite element models. It's an exercise engineers should always undertake to ensure as best they can that the computer model is outputting realistic and valid results. Next, there is a listing of the table of contents of the proposed report structure. Next, there is an outline of the full report. This is actually presented as 2 pages per slide of the presentation. This part of the presentation is purely to outline the structure of the report, the various headings used, and the essential content under each of the headings. But at this stage it will be quite difficult to actually read the text of the report. And basically that's the essence of this presentation, is just to show the structure of the report. If you do want to read the entire stress analysis report, I've tried to write it as professionally as I can to show how an industrial technical report would be produced. Then there is an enlarged presentation of the full report, which will be easier to read in the latter half of this presentation. And here are the approximate start times related to the various sections contained within the presentation, hopefully to aid your ease of access through the presentation, but please note these times are generally rounded to the nearest minute. So here's the presentation background. It relates to the analysis of a simple bracket, shown on the right hand side here. So essentially a colleague of mine modelled a simple bracket using a computer aided design or a CAD package. He then analysed the bracket using the inbuilt finite element software of the CAD package. He endeavoured to keep the loading as simple as possible for the analysis, so the bracket was loaded by a 100 Newton load, shown here on our sketch, applied to the top of the bracket. So that's a single concentrated point load. Fixations used, restraints applied here, around the whole edge on the base of the bracket. Just for reference, here's an enlarged view of the bracket showing the applied concentrated load of 100 newtons here on the upstand of the bracket, and the model restraints applied around the whole edge shown here. It was assumed that the restraints were applied around the whole edge in both translation and rotation. This right hand 2-dimensional sketch shows the applied load was actually at an angle of 15 degrees to the horizontal. Stress contour and deflection plots were then output from the CAD-FE analysis. And my involvement was to apply classical theory, what could be considered as hand calculations, to help validate the computer model. Once I produced my classical hand calculations using theory that HNC students and above would be familiar with, the CAD-FE model results and my classical calculations were compared and contrasted. I was then asked to produce a formal technical report, stress analysis report, and that's the essence of this presentation, to outline the structure of the report and overview the contents contained therein. And just for reference, this idea of trying to verify the CAD or finite element models is an exercise that's often undertaken within industry. We should always be cautious when using the output from CAD models that we do try and assess as best we can that the results obtained are valid. This is an illustration from many years ago, actually 1986. And this relates to the first model I was ever involved with. So this is an industrial illustration of the modelling of a turbine blade. On the left hand side we have the upper end of the turbine blade, which I think was called the tip shroud at the time. This was a three-dimensional model. And on the right hand side we have a two-dimensional model where we were trying to ascertain the contact stresses between a turbine blade and the disc of the rotor. But it's a left-hand side diagram I'm particularly interested here for this illustration. Essentially, this finite element model was used to calculate the centrifugal stresses set up in the upper blade. So figure 1, as it's termed here, this is an extract from the actual report produced. It shows the finite element model. It's actually a very crude model, as you can probably tell. But in 1986, our modelling capabilities were quite limited. We didn't have the extensive use of CAD, so the creation of models was actually quite difficult at that time. But anyway, just for background here, we did try to assess the computer model output to see if the results were reasonable. And I'm just going to show you an illustration of one of the checks we tried to undertake on this particular turbine blade. And this particular check relates to this location of the turbine blade. So essentially the hand calculation we tried to undertake was to use classical bending theory to evaluate the stresses shown here and here on this section of the turbine blade due to the centrifugal force of this portion of the turbine blade generating a bending moment about this section. So quite a crude calculation, but we're just trying to ballpark these stresses to see if the model results were producing stress levels of a similar value. So here's the industrial illustration continued. Here are extracts of the verification calculations we tried to undertake, trying to determine the bending stress due to the centrifugal effects of this small portion of the blade. I won't go through them in any detail, but basically we considered the blade to be cantilevered from this location here, shown here on my little sketch. So this was essentially the idealization or the simplification used within the verification process, within which we could apply the engineer's bending theory to estimate the bending stresses and so hopefully aid the verification of the finite element model. I just worked out the bending stresses in the top and the bottom of this section, shown here on the right hand side. So from the comparison at location A, top of the blade, the hand calculations produced a compressive stress, a negative stress here, of nearly 6,000 pounds per square inch. We were using imperial units, and the model produced a negative stress of around 7,000 pounds per square inch. So we were in a similar ballpark here. At location B, at the bottom of our section, our hand calculations produced a positive stress, a tensile stress of nearly 4,000 psi, and the computer results of around about 1,000. So these values didn't correlate too well. But this simple calculation here shows an insight into how engineers always try and verify computer models as best they can. Here's an illustration from a past student related to his design for a proposed workbench. The workbench is essentially an industrial table that can be found in a workshop and used for bench fitting or assembly purposes. This slide shows extracts from his technical report, showing a CAD FE model used to analyse the workbench under the two low cases of a downwards force applied and a lateral force applied. But on reviewing his technical report, I noticed there were no compressive or negative stresses within the computer output, which immediately had me slightly concerned because, of course, if we have a downward force on the tabletop, we would expect the legs to be in compression, we expect the tabletop to show some form of compression due to bending, and likewise if we have a lateral force applied to the side of the table, again we would expect to see the model show some compressive stresses within the table or workbench structure. So obviously that needed further interrogation. Why are there no compressive stresses in this model? So that was something the student needed to investigate and effectively try and verify the model. I'm not criticising the student here because he didn't actually have to undertake this exercise. He did this of his own volition, a highly motivated student, but was obviously very proficient using his CAD package. But then on using the inbuilt finite element software, he really needed to verify his output to ensure his results were as expected and so were valid. It was found the plots were actually related to von Mises stresses, and although this is beyond the scope of this presentation, von Mises stresses are always positive. So the point I'm trying to emphasise here is to always endeavour as best you can to validate CAD-FE models to ensure that the results produced are actually valid. I'm now going to briefly overview the report. In a moment I'll outline a proposed structure using a table of contents, and you might find this is a structure that you can use or modify when undertaking your own stress analysis calculations and presenting those in reports. In the first part of the presentation, quite difficult to read, the text is very small because for convenience I'm displaying 2 pages of the report on one slide. And that's because the essence of this first part of the presentation is purely to show you the structure of the report, basically outline the main headings and subheadings, and very briefly overview the contents under each of the headings. If you are interested in reading the full report, which I have tried to write as best I can in a professional manner as would be expected within industry, towards the end of the presentation I actually show the full report in a much more readable format. But for now let's consider an overview of the report and the structure used. So the first page states the title, Stress Analysis Report for the simple bracket here. This is sometimes called the title page of the report. Notice the report has a report number. All reports should have a specific number that they can be easily referenced within other reports or the documentation. And we have the author's name and we have the customer, sometimes called the client, stated as well. At the bottom of the title page we have an issue box, sometimes referred to as an amendment box, and for each of the issues of the report a very brief description is included to outline the status of the report at these particular issues. That's for the reader's reference. So that's the title page. On the right hand side we have what's termed the summary of the report. A summary is essentially an overview of the entire report from beginning to end. For example here from the background of the report right the way through to whether we considered the report to verify the FE-CAD model or not. The summary is usually written very concisely in 3 or 4 paragraphs. Summaries can be quite difficult to write because they have to be very concise but encapsulate the entire contents of the document. So here's the table of contents related to our example structure for the stress analysis report. The table of contents commences with main section heading 1, which is the introduction. Subsection 1.1 is the engineering drawing of the simple bracket, and we have up to section 7 contained within the report. So notice on the left hand side of the table of contents we have section numbers, main heading section 2 here, subsection heading 2.1, and the right hand side we have the page numbers. I should state that this table of contents is fully automated. I did not type this information in manually. I used headings within my word processing document, and the automated facility within the word processing package generated this table for me. I have seen some students actually type a table of contents in manually, but I would strongly encourage you not to do that. As I say, within most word processing packages this is an automated facility, but it also helps if you do update the report by inserting further headings or deleting some headings. Then again the table of contents can be automatically updated to reflect the new structure of the report. So on the following slides I'll now outline the structure of the report in a little more detail for ease of reading. So here's an enlarged view of the table of contents, easier to read. First section, number 1, is introduction. Remember, of course, we've already had the summary on the previous page outlining the full report, but the introduction states the objectives or the purpose of the report. And within this introduction I've also included the engineering drawing that my colleague produced of the simple bracket. I've also included the list of acronyms and definitions that are referred to within the report. For small reports, lists of acronyms are not particularly required. I've included it here for completeness. And definitions usually relate to specialised definitions that the general engineer may not be fully aware of, but specialist terminology is something that's useful to define at the beginning of the report. Section 2, we have an overview of the CAD-FE model my colleague produced. Subsection 2.1 is the bracket material properties. Section 2.2 is unity bracket conversions. I must say I would not usually put unity brackets within a technical report issued to an engineer, but as this report is specifically for educational purposes and aimed at HNC, HND students, I'm making aware of some of the relevant conversions that are implicitly included within this report. Subsection 2.3 here we have the CAD-FE model applied loading and restraints used by my colleague within the finite element analysis, and 2.4 is a summary of the results that were extracted from the CAD-FE model analysis. Again, left hand side are section numbers and right hand side here are the page numbers 5 through to 8. So here's the table of contents continued. This is now section 3. This relates to the classical calculations that I undertook. So section 3 is headed the classical calculations for both strength and stiffness. Subsection 3.1, I state the assumptions underpinning the theoretical classical calculations. Typical assumptions you'll see in most text or reference books, and also I've included specific assumptions related to the actual report. 3.2 contains the bracket section properties. These relate to calculations I undertook, calculating the various areas, second moments of area, etc., which are required within the stress analysis calculations. 3.3, I calculate the stresses in the bracket base at section B. For your reference, here is an outline of the model. So the applied concentrated load we know is at position A here, at the top of our bracket. And I'm now working out stresses at section BB. So effectively, I've idealised this portion as a cantilever beam, load at point A, fixed at point B. Subsection 3.4, then calculate the deflection of section A, assuming we are fully fixed at section B. So again, deflection of A relative to B. Section 3.5, calculate now the stresses in the bracket base. And that's defined as section B to D on our model. So section B through to D is the base of the bracket. Our hole cut out in section C. We then calculate the bending moment diagram for the section B to D. And then 3.7, we calculate the stresses for the bracket at section C. Section C shown here. And that's the section through the hole. That's referred to as the net section through section CC, whereas section through BB would be a gross section of the bracket. Subsection 3.8, we calculate the deflection, section BB, due to a force FB. This now assumes the bracket is fixed at section C. Now we're calculating deflection through here at BB, assuming the bracket is fully fixed at CC. Again, this is part of my idealisation, second cantilever beam here effectively. 3.9 calculates the deflection of section BB due to a moment MB applied. Again, this is all part of my breakdown of the classical calculations into what I consider to be a reasonable idealisation for mathematically modelling this particular bracket. And 3.10, we now have the estimated resultant deflection of point A, assuming we are fixed at section C. Calculating deflection of point A relative to fully fixed section CC. So that's section 3 of the report outlined. So the final part of the table of contents, section 4, was a comparison between the CAD FE model results and the results obtained through the classical calculations. Section 5 was the conclusion to the report, in this case considering the validity of the CAD FE model results. Section 6 contains references, so in this report there is actually only one that I've included. And then section 7 is the appendix. This includes CAD FE model information and stress plots that were supplied to me by my colleague. Just note an appendix, or indeed appendices, are additional information to the report. Usually appendix information is considered not essential to understanding the main body of the report and just supplied to give further background information as required. But for your reference, when I was a stress engineer working in the aerospace industry, my technical reports or my detailed stress analysis of various components may have a main body of around 20 to 30 pages, but I might sometimes include an appendix that has maybe 50 or more pages that contains background information that, although not required to understand the main body of the report, may be useful, for example, to allow the engineer to understand how the loads that are used within the main body of the report were actually generated, using various models, various spreadsheets, various assumptions, etc. Note that if you do include an appendix within the technical report, it must be referenced appropriately within the main body of the technical report. So that's the table of contents stating the various headings, subheadings I'm proposing for the structure of this technical report. I also included a table of figures in the front of the report. The table of figures was automated by the word processing package, so I didn't type this table in. It automatically generated this table because I use captions for my figure numbers. So all my figures are stated here, 1 through to 14. And I also generated a table of tables. Again, this is an automated feature. I didn't type this information in. I used captions for my tables, so the processor automatically generated this table of tables for me. And again, sometimes in reports it's very useful, particularly lengthy reports, to have the table of figures and the table of tables included. So now I'll briefly outline what's termed the main body of the report. Again, you'll find the text quite difficult to read because I'm showing 2 pages of the report on one slide. But that's not the purpose of this part of the presentation. The main essence here is to show you the structure, basically the headings again that's in the table of contents, and outline briefly the contents under each of the headings. As I said, if you do want to read the full report in detail, the report will be presented in a much more readable format near the end of the presentation. So here we have main section heading 1, with the introduction, main purpose or the objectives of the report. And remember, of course, we've already had the summary which outlines the full report very briefly. So essentially here this report is really for educational purposes. It's aimed at higher technician engineering students and essentially trying to show them how to undertake the verification process of a CAD FE model, using theory that they should be familiar with following their studies of Higher National Certificate or Higher National Diploma. Subsection 1.1 shows the engineering drawing of the simple bracket my colleague produced. This is a 2-dimensional drawing that was generated from the CAD model. And subsection 1.2 here states the list of acronyms and definitions. It's sometimes useful, particularly with large reports, to actually have a list of acronyms near the front of the report, just for convenience of the reader. They're usually listed in alphabetical order. And sometimes it's also useful to state particular definitions or specific terminology that is used within the report that the general engineer might not be aware of. The general convention with use of acronyms is to define the acronym in the text when it's first used, but as I said, sometimes it's nice to have all the acronyms listed in one particular section. It makes it easy to find if you have a very large document with an awful lot of acronyms. So sometimes it's difficult to find where it was first defined, so having a list is convenient. So just for completeness, I tried to state various acronyms that are used within documents, so CAD, FE, HNC, and also SI. That relates to the International System of Units, sometimes referred to that as the SI system, but it really should be called the International System of Units. That's a system we should always be using within our modern reports. And I have actually stated some definitions here. When I refer to a beam simple support within my analysis, I mean the support is considered to be restrained in translation only. Translation means movement in the X, Y, and Z directions. And I've also stated the definition for a beam with a fixed support, sometimes referred to as fully fixed or built-in support. This relates to the support being restrained in both translation and rotation. In other words, we're not only restrained in movement in the X, Y, and Z directions, but we're also restrained in rotation about the X, Y, and Z directions or axes. And purely for your reference, I've just added an enlarged version of the side view of the bracket here, showing the dimensions slightly more clearly. Just notice here the bracket width is actually 50 millimeters. That's determined from the radius here of 25 millimeters. Section 2 is an overview of the CAD model that my colleague produced. Again, a very brief introduction. The CAD model in this case obviously relates to our simple bracket. I've stated the bracket material properties. We will need material properties. I've just extracted these from the CAD FE model. They're slightly different to perhaps I might be using if left to my own devices, but I needed to use the model properties. Notice I referred to the appendix here, where these particular values can be found. Section 2.2 is my Unity bracket conversions. As I said, in a professional technical report that I was issuing to other engineers, I probably wouldn't include this type of information, but because this is aimed at technician engineering students, as you may know by now, I'm quite keen on the use of Unity brackets, so I've included Unity bracket conversions from megapascals to newtons per millimeter squared and vice versa. Again, it's purely for reference. There's a separate presentation on Unity brackets if you're interested in viewing that for further information. Section 2.3 shows the CAD FE model, applied loading and restraints. The applied load of 100 newtons at this point here and 15 degrees horizontal, and the restraint shown around the hole edge. On the right hand side of the slide, here's another page extracted from the technical report. This shows section 2.4, which is a summary of the results that were extracted from the CAD FE model analysis. This slide just highlights some of the main stresses and deflections. And then section 3 starts with my classical calculations for the strength and stiffness estimates for this bracket section. Again, I introduce the section, state my assumptions. As with any theory, there are underpinning assumptions, so these are the assumptions that I'm using for the classical theory. Standard assumptions you'll find in most text or reference books, but I've orientated some of the information directly to this particular report. And section 3.2 have my bracket section properties. So I have section properties related to what I term the gross section. That's a section away from the whole area. And I have next section properties. That's a section through the whole. Again, purely for reference, I've added this side view of the bracket to the slide here. So when I refer to the gross section properties, that relates to a section of the bracket having the full width of 50 millimeters. Think of that as being 50 millimeters out of the page, out of the slide. Gross section properties would be through section BB, shown here. And what is termed the next section properties, and the net section is through section CC, shown here, where material is lost due to the hole cut into the bracket, is actually a section that's 50 millimeters width, but has the 20 millimeter square hole removed. Subsection 3.3 relates to the stresses in the bracket base at section B. I added these sketches in the centre of the slide here for your reference. So we're calculating the stresses at section BB, shown here, due to the force applied up here through section A. So this is the force at A, labelled FA. And this cantilever beam approach here is an idealisation, of course, but hopefully something that HNC, HND students will be able to relate to. So essentially we calculate the bending stress at location B, and this value is then being compared to that from the CAD-FE model, and we find a 38% difference between the two values. Section 3.4, we then calculate the deflection of point A. Again, we're assuming we're fully fixed at section B, so now deflection is position relative to B. To undertake this calculation, I'm going to use a standard beam formula extracted from a very familiar industrial reference source, labeled as reference 1 here. This reference source is full of standard beam cases, so here's my standard beam case, and the formula is stated in the table below, repeated here. From this formula for the cantilever beam, I can calculate the deflection of A relative to B. Next page of the report, and subsection 3.5, this relates to stresses in the bracket base. That's defined as sections B to D. So we're finding the stresses in this base of the bracket here, B through to D. To analyse this portion of the bracket, I've now considered a simply supported beam here. So simple supports at section C and D assumed. And my applied loading is at section B. Essentially a point load, FB. I have an axial load, a tension load, PB. And I have a pure moment or pure couple, MB, applied at location B. Calculation for the loading, shown here. Again, I realise this is difficult to read, but if you do want to read and follow the calculation in detail, remember there is an enlarged view of this report towards the end of the presentation. Using the principle of summation of moments, I calculate reaction RC. Using the upwards and downwards force equilibrium equation, I calculate reaction RD. And then I can calculate the bending moment at C, which I've actually undertaken using two calculations, calculating moments to the left of point C and then calculating moments to the right of point C. And of course I get the same value, which I should do because that shows my beam idealisation is in equilibrium. Subsection 3.6, now calculating the bending moment diagram from section B to D. So the bending moment diagram for this section, that's based on the calculations from the previous page. We then undertake calculation for the stresses in section C of the bracket, so calculating stresses through this section. Actually the net section. I have calculated gross and net section stresses here, but it's really the net section stresses we're interested in. So I've calculated the net bending stress here. I have actually considered tensile stresses. I've got the net tension stress shown here, but what we find is the tension stresses are almost negligible compared to the bending stresses. Again, I undertake a comparison between the CAD-FE model results and the classical calculations shown above, and the difference is times about 12%. Next page of the report, section 3.8. Now calculate the deflection at section BB due to force FB. What we're now assuming is that the bracket is fully fixed at location C here. So I've a cantilever beam from C now. And again, I've used a standard deflection formula here from our reference source, deflection location B, subsection 3.9. I've calculated the deflection of section BB due to the moment MB applied at B, again using standard deflection formula, or the beam scenario we're considering, so from our standard reference source. And subsection 3.10, now estimated the resultant deflection at point A, assuming the bracket is fully fixed at section C. There's our resultant deflection of point A now relative to point C. Next page of the report shows section 4, and this is now the comparison between the CAD-FE model and these classical hand calculations. The comparison based on the strengths analysis and the stiffness analysis that's been undertaken. And section 5, we now have the conclusion to the report, essentially from the calculations undertaken and the comparison between CAD-FE model and the classical calculations. We state whether the model has been reasonably verified. In this case, I did consider that classical calculations help to verify and essentially give us confidence in the model produced. The model analysis, of course, should be much more accurate. But using our classical calculations, we've deduced that we're in the ballpark of the results the model has output. Section 6 shows the references. There's actually one in this particular case that I've used, and that's the end of the main body of the report. As I said, I did include an appendix. Section 7 is the appendix in this particular case, showing the CAD-FE model information that my colleague supplied to me. So that concludes the main purpose of the presentation, to show you a technical report structure that hopefully you could use and modify if you're undertaking similar kind of analyses and trying to verify output from CAD or finite element models. If anyone is interested, I will now show the enlarged version of the report. This is the full report, so I've broken down into sections that should be easy to read on the slides. This is only really for if you're really interested in the detailed analysis I undertook. I'll basically let you read this at your own pace. You can stop the presentation as you need to or browse through it however you consider best. This is an extract from the title page, stress analysis report for our simple bracket. As I said before, you should always have the report number on the bracket, the author, in this case the client, the customer. And I got my amendment or my issues. Issue 1 was the first release, issue 2 was the appendix now added, and issue 3 minor terminology and formatting updates. So essentially this is useful to the engineer. They may read the first issue in full, then when the second issue is given, we can clearly see that it's only the appendix that's been added. So when they decide that they don't really want to read the report again, because the appendix should be additional information that's not required to understand the full report. And then the same with issue 3, the minor terminology and formatting updates. Again, an engineer would probably skip that issue because nothing significant seems to have changed within technical aspects of the report. So that's why it's useful to have the issue table, very brief description of what the revised version or the change in issue relates to. For traceability, each of the pages of the report has the title of the report, has the report number, and also the issue number, issue 3. And that's for traceability. So a report should have the issue number to show that you're using the most up-to-date information. So here's our summary. You read this at your own pace. And here's the continuation of the summary. Here's page 3 of the report, stating the full table of contents. Again, section numbers on the left-hand side, page numbers on the right-hand side. Table of figures. Table of tables. Here's the introduction, page 5 of the report. Here's the CAD drawing my colleague produced. Page 5 continued, subsection 1.2. Here's our list of acronyms and definitions. Acronyms shown here, definitions shown here. Section 2 is the overview of the CAD model and bracket material properties, shown on the next slide. And here they're extracted from the CAD-FE model. Here's our unity bracket conversions, Again, I would not normally add these into a formal technical report issued to an engineer, but as this is an educational document effectively, I have included them here. Section 2.3, CAD FE model applied loading and restraints shown here. You see concentrated applied point load of 100 newtons in its location here. Here are the restraints around the hole in the bracket. Page 8 of the report, subsection 2.4. Here's the beginning of the summary of the results extracted from the CAD FE model analysis. These show stresses in the Y direction from the CAD model. Section 2.4 continued, again showing stresses in the X direction, extracted from the model. And there's a deflected plot, shows the deflections, the maximum deflection estimated at 6 millimeters. At this location here, on the top of the bracket. In section 3 is the classical calculations for strength and stiffness, my hand calculations here. Section 3.1 on page 9, the assumptions for our classical theory. Assumptions continued here, still page 9. Section 3.2, bracket section properties, which were calculated by me. These are the gross section properties we mentioned before. Gross section properties would be through section BB shown here. And we have net section properties, that's from section C. And the net section is through section CC shown here, where material is lost due to the hole cut into the bracket. Page 11 of the report, subsection 3.3, stresses in the bracket base at section B. This is our cantilever beam idealization. Here the stress calculations would be through section BB shown here. Page 11 of the report continued, subsection 3.4, deflection of section A, assuming fully fixed at section B. Again, this is extracting a standard formula from our reference 1 for this particular beam case shown here. Here's the standard formula, shown without proof. Page 12 of the report, 3.5, stresses in the bracket base. This considers sections B through to D. So section B through to D is the base of the bracket, the hole cut out in section C. 3.5 continued here, calculating the loading applied at section B. Then we calculate the reaction RC, considering moments about section D. Taking moments about D, we find RC. Section 3.5 continued. Then we calculate reaction RD by summating vertical forces. Then we can calculate the bending moment at point C, and here, which I actually undertake a check on. I consider bending moments to the left of C and then to the right of C, and of course we should get the same answer in both cases, which we do, so it shows we're in equilibrium. Again, this is a theory that engineers would most likely have covered in previous units, previous lectures. Section 3.6 shows the bending moment diagram for sections B to D. So from B through to D here. Page 13 continued. Subsection 3.7, stress calculations for the bracket at section C. It's the net section stresses we're interested in, net bending stress shown here. And the net section is through section CC shown here, where material is lost due to the hole cut into the bracket. And we've also calculated the net tension stress here, but notice how the net bending stress is significantly more than the net tension stress. In other words, the net tension stress is negligible compared with the net bending stress. Section 3.7 continued. Again, we have a comparison now between the CAD FE model and the classical calculations. There's a 12% discrepancy shown here. Page 14 of the report, subsection 3.8, calculating the deflection at section BB due to force FB applied. We're now assuming that the bracket is fixed at section CC. Now we're calculating deflection through here at BB, assuming the bracket is fully fixed at CC. So again, this is part of my idealization, second cantilever beam here effectively. Again, we're using a standard beam formula from a reference source shown here. Page 14 continued, subsection 3.9, calculating deflection of section BB due to the moment, MB applied. Again, we're assuming that section CC is fixed. And again, using our standard beam case, we have a standard formula to use from reference 1. And page 14 continued, subsection 3.10. This is the estimated resultant deflection of point A, assuming fully fixed at section C. So calculating the overall vertical deflection of A, calculating the overall horizontal deflection. We use Pythagoras' theorem here to calculate the resultant deflection. Again, this is all based on the idealization. So calculating deflection of point A relative to fully fixed section CC. If you do review this part of the presentation and the detailed part of the report, you may actually find a preferable, more representative idealization that you could apply to this particular situation, and that's fine. I'm just trying to indicate how engineers go about trying to verify CAD FE models. Here's page 16 of the report. Section 5 is the beginning of the conclusion. Conclusion continued here. The final part of the conclusion. Overall, I considered that we reasonably verified the FE model results, so I would have reasonable confidence in using the computer analysis. Here's section 6, which is the reference. Just one reference in this case. And that concludes the main body of the report. And finally, here's the appendix. I've shown it in full here, but probably difficult to read because they're just snapshots of the original work. This is XX stresses in the bracket. There's information of the CAD model. Though it's difficult to read, these are actually the model properties that I was given. And I added more information to the appendix here. Stress plots. So that concludes the presentation, which I hope has been of some interest to you, and as always, thank you for viewing.